Let's work through a few examples from 5.2. So in 5.1, we looked at taking the derivative of natural log. And the derivative of natural log is u prime over u. So if we think about integrating this, the derivative and the integral cancel. On the right side, u prime is essentially du, and we have u on bottom. So when we integrate du over u, the answer to that is natural log u. One thing we have to be careful with is when we take the natural log or log of any function, we can only take the natural log of positive numbers. So to ensure that, we put absolute value around it. And then remember from basic antiderivatives, they give us a family of solutions, so we have to have a plus c on there as long as it's in indefinite integral. So one of the biggest parts of this section is that formula. If we have a function on bottom, the derivative of that function on top, then that integrates into natural log. So for example, if we have 2x plus 5 on bottom and 2 on top, if we were to let the bottom be u, then du, the derivative of this, is 2, so du would be 2 dx. So notice this whole thing is du, this whole thing is u. So if we're integrating du on top, u on bottom, that equals natural log absolute value of u plus c. So in place of the absolute value, we'll put 2x plus 5. Now, if you recognize you have du over u, you don't necessarily have to write this middle step. The more times we use this substitution, the less likely it is that you show this middle step. You're free to go from here to here. Sorry about that, my alarm was going off in the background. So let's look at another one. Let's suppose on bottom we have x squared plus 5x, and on top we have 2x plus 5. One of the keys in all of these that integrate into natural log is that the degree on top, if these are both polynomials, the degree on top is exactly 1 less than the degree on bottom. So this degree is 1, this degree is 2. Why is that important? Well, if we let the denominator be u, then when we use the power rule to take the derivative, our exponent goes down by 1. So the derivative of the first term is 2x. The derivative of the next term is 5. So 2x plus 5 dx, that is du. So there's our du. That's u. So that integrates into natural log absolute value of u. And u is x squared plus 5x. And then we have our plus c. Now, occasionally, we'll run into a case where we might not have the same coefficient on top, might not have the coefficient we need. For example, if we let the denominator here be u, then du would be 4x cubed dx. Excuse me. So we have the x cubed in the dx part. What we don't have is the 4. But we've illustrated before that we can fix that. As long as we multiply this by 1, it doesn't change how much we have. So if we multiply the top by 4 and multiply the bottom by 4, we're still equivalent. We don't need a 4 on bottom on the inside, so we can put the 4 on bottom on the outside. That's equivalent to our original problem, because if you think about it, those are common factors, they would cancel. But we're not going to cancel them, because the whole reason of putting the 4s is because we needed this 4. So now that's du, that's u, so we're integrating du over u. So our answer is 1/4 times natural log absolute value of the denominator. plus c. Now sometimes you might see your answer written differently. You might see it written like this. And you might say, well, why write it like that? The formula for natural log, excuse me, the formula for integrating du over u is natural log of the absolute value of u plus c. Well, the absolute value is for the purpose of guaranteeing that that is positive. If this expression is always positive, if there's no time where it's negative, then the absolute value is not necessary. When we raise any number to an even power, that's always positive. And if you take a positive number and add 3, it's still positive. So in this case, the absolute values are not necessary because that is going to be positive regardless of what x is. So I would be fine with either one of them. If you happen to put the absolute value in and WebAssign says, oh no, that's not right, well, look to see if what's inside is always positive. If it is, drop the absolute value and see if it gives you credit for it. If it doesn't, then there might be another mistake that you've made. All right, so going on, occasionally we'll end up with something like this. Let's do, and in this case, notice the degree on top is not 1 less than the degree on bottom. So if we let the denominator be u, the derivative of the denominator would be 4 dx. Well, we don't have just a constant on top. We've got x squareds. So in the case that the degree on top is not 1 less, it's not just going to work out to be natural log right from the beginning. This is actually referred to as an improper fraction. Now, we may have discussed that in algebra before, but the first time you ever hear about an improper fraction is when you first learn about fractions and you have a number that's larger on top and a number that's smaller on bottom. That's referred to as being improper. Here, it's not so much the numbers as it is the degree. The degree on top is larger than the degree on bottom, so that's considered to be an improper fraction. So the way we fix that is we have to divide it out. Fortunately, this one is a monomial, so we just take the numerator divided by each term in the numerator and divide by the denominator. So this x will cancel one of those x's. So we can integrate each term separately. We can integrate x over 4, or we can call that 1/4 x, and put our dx with it. And we can integrate the next term. We could call that 5/4 over x, or we could put the 5/4 in the front. We could call that 1 over x, or we could call it dx over x. 5/4 is just a coefficient, so we can put the coefficient in the front. We have an x on bottom, dx on top. So when we integrate the second one, we leave our coefficient out front. Dx over x is natural log absolute value of u, where u is x. For this one, 1/4 is a coefficient. The integral of x is x to the second power over 2. So that gives us x squared over 8 plus 5/4 natural log absolute value of x plus c. Let's suppose we have this over x minus 2. Suppose we have this one. The degree on top is larger than the degree on bottom, so this is an improper fraction, so we need to divide it. But we have more than one term on bottom. So if we have more than one term on bottom, we don't just simply divide each of these by x minus 2. We either have to use long division, or since the denominator is a linear binomial, we can use synthetic division. So remember, with synthetic division, we list the coefficients. We put the divisor out front. So if we're dividing by x minus 2, remember we put a positive 2 in the box. We're putting whatever makes the divisor equal to 0. That's what goes in the box. And then we bring down a 2, multiply times the box. Add that column, multiply that times the box. Add that column. The last number is the remainder. This is the constant, and that's the coefficient of x. So 2x minus 3 is the quotient. The remainder is 3. So the way we can rewrite our polynomial, or not our polynomial, our fraction, is the quotient plus the remainder over the divisor. The quotient plus the remainder over the divisor. So now we just integrate each term. For the first term, to integrate x, it's x to the 1 bigger power over that power. For the next term, to integrate a constant, we pick up our variable. And for the next term, to integrate 3 over x minus 2 dx, the denominator is u. So du would be 1 dx. We actually have 3 dx. So that 3 is not needed, so we can just move it out front because it's just a constant. And then we have 1 dx, or dx, on top. So this is du over u. So when we integrate that, we have a 3. Natural log absolute value, remember the integral of du over u is natural log absolute value of u, with a 3 out front. And let's see on the end. Here the 2's cancel, so this would be our final answer. The absolute values are necessary because depending on x, sometimes what's inside there does come out to be negative. So we do have to have the absolute values for this one. In this section, if you watch the videos that went with WebAssign, you may have picked up on that there were 4 new antiderivatives in this section. In the past, we've known how to integrate sine, and we've known how to integrate cosine. What we've not been able to do is secant, cosecant, cotangent, and tangent. So I'm going to illustrate one of these, and then we'll just provide the integrals for the other ones. So why can we do these now, or if so, why can we? So if we look at tangent, another way of writing tangent is sine over cosine. If we were to let the denominator be u, then the derivative of that is minus sine x dx. So if we were to put a minus here and a minus here, then we have du on top, u on bottom. U, and that's du, which that integrates into natural log absolute value of u plus c. So u is cosine x. And we have the negative out front. So that's the integral of tangent. Negative natural log absolute value of cosine x plus c. If this is not just x, then we would just change that to u, and that would have to be du. So whatever is on the inside, this would have to be the derivative of that function. So the same thing with the same type of thing works with cotangent. Cotangent is cosine over sine. So this one turns out to be natural log absolute value of sine plus c. Cosecant, that one's a little bit messier to show, but it turns out it's natural log absolute value of cotangent plus cosecant plus c. And secant is natural log absolute value of tangent plus secant plus c. Remember from other derivatives and antiderivatives we've done, the cotangent and cosecants normally kind of go together. The derivative of cotangent is cosecant squared. The derivative of cosecant is cosecant cotangent, or negative cosecant cotangent. And same thing with tangents and secants, they normally go together. So let's do one of these. If we want to integrate cosecant, well, let's do secant. Secant of 3x dx. Well, this part needs to be the derivative of that part, because our formula generically is secant u du. If it's just x, then that's okay to be dx. But if this is not just x, we have to do kind of like the chain rule or do a substitution. So whatever this is, that's the derivative of it. So that still integrates into natural log absolute value of tangent plus secant plus c. So if u, that's the inside of secant, if that's 3x, du would be 3 dx. So we would need a 3 to go with the dx, and if we multiply there by 3, we divide there by 3. So we have 1/3 the integral of secant u times du. So that integrates into 1/3 natural log absolute value tangent u, which u is 3x, plus secant u plus c. So we just have to make it fit the formula. Whatever this is, that's u, because we're integrating secant of something. So that's u. That has to be du. So if it doesn't match du at the beginning, make it match if we're missing just a coefficient.